first thing I want to do is kind of walk you through this homework, kind of make sure we understand how to do a complete model for the chi-squared write-up. Okay, so here we go. After getting trounced by your little brother in a children's game, you suspect the die he gave you to roll may be unfair. To check, you roll it 60 times and recording the number of times each face appears. Do these results cast doubt on the die's fairness? All right, so essentially, you will have an entire phantoms model, but you will not do the P part of the phantoms model. So, phantoms, I guess. Because there is no parameter. There's no parameter of interest to do. So, since we don't have a letter like a mu or a T to write up, then we end up just using words when we write our null hypothesis. Okay? But the first question here is, if the die is fair, then how many times of those 60 would you expect each face to show? And that'd be 10. Okay? So on average, as you did bunches of sets of 60s, you'd expect it to be about 10 times each. All right. To see if these results are unusual, will you test goodness of fit, homogeneity, or independence? We learn homogeneity and independence tomorrow, so this is obviously chi-squared goodness of fit. All right. So, yes, when you state your hypotheses, they are actually in words because you do not have any symbols for this problem. You don't have a mu or a p. So the null hypothesis is that the faces of the die are all equally likely. So you start off saying, okay, yeah, they're going to all happen about the same amount. And then see if you have evidence to reject that for the alternative that the faces of the die are not equally likely. Okay? All right. So the next part is conditions. And as we found yesterday, those are the same conditions we've been doing, random, independent, large enough. Large enough is a little bit different than what we've seen, but let's go through those. Okay, so for your conditions, you're random. You're going to assume that a die roll is random. I think that's reasonable. I think that's kind of one of the reasons you do the die roll, is so that it is a random event. Okay, and then independent, that is that our sample size, which is 60, is less than 10% of all the die rolls that we would be doing with this die. And then large enough. So our large enough is different than we've had in the past with Z curves and T curves. So what's that going to look like? Do you remember large enough? No, not all probabilities are greater than. Okay, you had to do your percent of success times the total, because that gave you then what was expected. The key is that, yes, your expected value, what you expect to happen for each category, has to be greater than 5. So in this case, you had told me in the first problem up at the top that the expected was 10. So here, expected counts for each number, which is 10, it's greater than 5. Yes?
Our independence, how do we know that 60 is less than 10%?
Well, I'm kind of just, I guess, in a sense, making an assumption that I could roll this die a whole bunch more times, and that the 60 is less than 10% of all the times I could roll this die. Okay? All right, so you know at the end of our other conditions, we summarize with saying the normal model applies or the nearly normal model applies. Well, here, what kind of model do we have? The chi-squared model applies. Okay, so you're going to summarize your conditions saying that the chi-squared model applies. All right, so, yes.
Why is it so important that chi-squared?
Okay, the reason that chi is squared is because yesterday, if you remember when we did our components, they had to all be positive so that they did they didn't cancel each other out when they totaled to be a chi-squared. And so that number is just traditionally left squared. You could square root it, and depending on the size of your test, if it was only 2 or 1 sample, it could look just like a z-score. Okay, which is kind of another beyond what we're talking about. So there you go. We'll come up with that problem. That's actually kind of a cool problem I want to show y'all sometime. Okay, so we checked our conditions, and then our degrees of freedom are not 60 minus 1, but 6 categories minus 1. So our degrees of freedom are 5. Remember, the degrees of freedom tell you which curve to look on. There's a whole bunch of chi-squared curves, just like there's a whole bunch of t-curves. Okay? All right, so then you go compute your chi-squared and your p-value. Now, what I actually did was went and put this information into my calculator. So I put this observed counts into L1, okay, and then I put the expected into L2, and then I ran the chi-squared goodness of fit test, not just plain chi-squared, okay, and then those are the values I got, and you don't need to compute that right now necessarily unless you want me to help you figure that out. Okay, and do list also your degrees of freedom, just like we did with t-tests, to say which curve to look at. All right, now let's make the conclusion, and let's state it the way that we've been stating that this year. And so what we would do is start off with, since our p-value, which is 0.347, is greater than alpha, then what's our decision going to be? Okay, we're going to fail to reject, okay? So I will fail to reject the null hypothesis. And so you're restating that null hypothesis, which that null hypothesis says here. So I am not rejecting that the faces of the die are equally likely. I do not have evidence to reject or dispute the die's fairness. Okay, so I'm not rejecting that they are equally likely. They could be equally likely is what I'm saying. So here I go. Well, sort of kind of notes, because it's going to be the first part of what you're doing there. So since p-value is greater than alpha, I reject that I fail to reject that the faces of the die are equally likely. So now we then talk about having evidence for the alternative and answering the question. The question being this: do these results cast doubt on the die's fairness? What do you think? We don't have evidence to reject its fairness, so I don't have the ability to have statistical evidence to doubt its fairness. So that kind of statement would look like this. These results do not, and a lot of people kind of like that, give evidence of. So these results do not give me evidence to cast doubt on the die's fairness. I did not have evidence to say that is a messed up die. Okay, if you did have evidence, then your chi-squared number would have been bigger, and you would have had a small p-value. You know, it would have been less than alpha. Okay, so less than alpha, if your p-value was less than alpha, I would have rejected the null hypothesis. And the null hypothesis says the sides are equally likely. So if I reject that they're equally likely, then I'm saying, whoa, something's messed up here. They are not equally likely. Okay? It is the same standard. It didn't state, so I used the standard of 0.05. Okay, that's the same default. Okay, so that's all of that one. Now what I want to do, I'm actually going to split this thing in half.